Hi there, and welcome to Raylene Math. This is the first video in a series of videos on sequences. In this video, we will look at the prerequisite knowledge, the prior knowledge, for understanding sequences, what they are, and how to use them to proceed onto series and Taylor series. In the first question, the warm-up, we want to use the factorial notation to evaluate 5 factorial. So 5 factorial is defined to be 5 times 4 times 3 times 2 times 1, and we can see that this is equal to 20 times 6, or 120. In the second example, we can just use the definition again and get 120 divided by whatever 3 factorial is, but we can use the definition of 5 factorial to be 5 times 4 times 3 factorial. And so we will write this as 5 times 4 times 3 factorial divided by 3 factorial, and then we can reduce the fraction. We always want to reduce fractions wherever possible, and this answer is 20. Of course, 3 factorial is 6, and 120 divided by 6 is 20. Using this expansion and reduction technique of part B, we can express something like n, where of course n has to be an integer value to use this definition. And so n factorial is n times n minus 1 times n minus 2, etc., which is n times n minus 1 factorial, divided by n minus 1 factorial, and we reduce to leave us with just the initial integer n. Now we want to take a look at some functions. We are going to be doing some connections between continuous functions and discrete sequences. And so let's look at the function values here for 1 over x to the q. So we'll draw some graphs. We're going to define them for x greater than 0, so I don't need the left side of the xy plane. And so we have a simple graph, for example, would be if q is equal to 0, and then we know that x is equal to 1 over 1. So I'm not going to label this the function f of x equal to 1. Instead, I'm going to label it by the value of q that produced this graph. So if we have q, we have x to the 0 is 1. 1 over 1 is y equal to 1. And then if we take q is equal to 1, we get 1 over x to the 1, which is the 1 over x, or reciprocal function. And so I'm going to label that with a q value equal to 1, which is the function y equals 1 over x. And then if q is equal to 2, we get the reciprocal square function, which would be here in quadrant 2 or here in quadrant 1. It's a little bit sloppy looking, like this. And it's a bit hard to see, but that green graph does lie underneath the red graph. I'll take it slower. And then we have if q is equal to, and so I'll label this q is equal to 2, which gives us the graph y equals 1 over x squared. If q is equal to negative 1, then we have 1 over x to the negative 1, which is just y equals x. And so all of these graphs are intersecting at the point 1, 1. I could put the rest of the graph there, but we're only defining it or graphing it for x greater than 0, so I will only consider the right-hand side of the x-axis. And I will label this q is equal to negative 1. And lastly, if q is equal to negative 2, we are going to get a parabola, and the parabola graph do it in orange, also passes through 0, 0, and looks like this. So we have 5 different graphs. We have red, orange, blue, green, and purple. So then we want to know what the graphical significance of this expression, limit as x approaches infinity, on any one of these graphs is, and the notation here is talking about the right-end behavior. So the right-end behavior is the behavior that the graph has when we zoom out far enough on the right-hand side. And we can see that the blue graph is a constant function, so for that function y is approaching a height of 1. The purple and the orange graphs are increasing functions, and so as x approaches infinity, y on both of those graphs, the height that y approaches, is equal to positive infinity. But for the 2 decaying or decreasing functions, the red and the green ones, as x approaches infinity, y approaches 0. And so we are looking at the end behavior, the zoomed out behavior, and different functions behave differently. We see 3 different types of end behavior. And then lastly, for what values of q does the limit equal to 0? Well, we see that it's the case for the red graph and the green graph. So the red graph says that the limit as x approaches infinity of 1 over x to the 1 is equal to 0. That was consistent with a q value of positive 1. And then the green graph says that limit as x approaches infinity of 1 over x squared is equal to 0. And that was valid for the q value of positive 2. Now we're going to introduce a few other functions that are not just continuous functions. We're going to introduce this combination of a power function and an exponential function, as well as a factorial function. But we first need to make sure we understand the difference between a power and an exponential function. Let's consider the statement 2 cubed equals 8. A lot of people read this as 2 to the power 3, or the 2 to the third power is equal to 8. This is a bit misleading because it leads us to think that the power is 3, but the power is actually the output of the exponential statement. The 8 is the power. And so we're going to get a little bit picky about the language here and call this base raised to an exponent is equal to the power. Try, if you can, to refrain from saying 2 to the power 3, because that reiterates or informs that the power is 3 when it is not. The exponent is 3 and the power is 8. More on this if you want to see in other videos on exponential functions. So when we talk about a power function, we are talking about a function that has a variable in the base and a constant in the exponent. So things like x squared, or the cube root of x, which can be written as x to the 1/3, or 1 over x to the exponent 2, which is x to the negative 2. So the variable is in the base, and the exponent is a constant. Similarly, when we deal with exponential functions, we have things like 2 to the x, or 1/2 to the x, which is an exponential decay, or the natural base e to the x. And here we have that the variable is in the exponent, and the constant is in the base. And we should be very comfortable knowing that exponential functions grow much faster than power functions. If we take a look at an example, we can take a look at x squared versus 2 to the x. We see that the x squared function, the parabola function, if we zoom back to kind of a standard zoom window, we see that the blue function is initially lower than the red function, but at some intersection point they meet up, and then the blue function, the parabola, the power function, takes over. But if we go to a different zoom, we see eventually that when x is even 10, that the blue graph is much lower than the red height. We can't even see the red height. We'd have to really zoom out and see that the red graph is very high relative to the blue graph for x equal to 10. So this is an indication that the slope, or the rate at which the red graph is changing, the derivative, is much bigger eventually than the power function graph. And eventually, in this particular example, isn't x approaching infinity. It already occurs at x equal to 10. So now that we've established that we have exponential functions growing faster than power functions, we can look at ordering them from slowest to fastest growth rate, or smallest to largest. So we know that the exponential function, a base raised to a variable exponent n, is going to be faster than the variable to the exponent, the power function. But what about this hybrid function? A hybrid function is a combination of having the variable in the base and in the exponent, and so we can see that makes sense that it should be faster than either one of these. But let's take a look at each of these separately. Let's take a look at the power function. Let's call a power function like 3 to the n. We are now replacing the constant or continuous variable x with the discrete variable n. So n is an integer, whereas x was a real value. So 3 to the n is not the one I want. I actually want a power function first. So if we take a power function like n cubed, this is going to be n times n times n. And if we have an exponential function, like 3 to the exponent n, we're going to get 3 times 3 times 3 times 3 multiplied by itself n times. So if we wanted to continue multiplying something in the first case n times, the rest of the numbers each would have had to been 1. And then if we take a hybrid, Now this is not a technical term, but it's a combination of power function and exponential function. And so this would be n multiplied by itself n times, where n is an integer. And then the factorial expression, n factorial, is going to be n times n minus 1 times n minus 2 multiplied all the way down to 3 times 2 times 1 at the end. And so I've tried to line up all of these terms. So we can see it looks initially that the power function is going to be faster than the exponential function in the end behavior case. We're specifically looking for n approaching infinity. So for n approaching infinity, we see that the power function is going to be bigger than the exponential function. And in fact, it's going to do that for the first three comparisons. However, if n is going to infinity, we're not just multiplying n by itself 3 times. We're multiplying n by itself an infinite, or 3 rather, by itself an infinite number of times. So we have to look at the entire snapshot of output values. And so we're going to get n is greater than 3, n is greater than 3, n is greater than 3, but then 3 is going to be greater than 1, and this is an infinite number of 3's, and 3 to the infinity is infinity. So that's why the exponential function is greater than the power. If we look at the hybrid compared to the exponential function, we have the same number of factors because we're multiplying something by itself an exponent number of n times. But what we're doing is comparing multiplying 3 by itself an infinite number of times versus the base n an infinite number of times. And each time, the n from the hybrid is going to be bigger than the 3 from the exponential function because n is approaching infinity. Obviously, if n were approaching 2, then the exponential function would be bigger, but the hybrid case wins in the end behavior limit. And so then if we compare the factorial to the hybrid, we can see that we still have n factorial is going to be n times itself, or times the other factors, which is a total of n times, n number of factors. And so we can compare each of these one by one. And for the first three, we know enough about end behavior of continuous functions to know that this limit is equal to 1, and this limit is equal to 1, and so on. All these different possibilities of linear over linear is going to give us an end behavior or a horizontal asymptote of y equal to 1. But eventually, the factorial terms stop being with n's and they become things like 3, 2, and 1, whereas the hybrid terms are still n times n. And so the behavior here shows that the hybrid is going to be faster growing than the factorial. So when we put all of these in order from smallest to largest, we have the power function is the slowest growing, then the exponential, then the factorial function, and lastly the hybrid function. But this is, again, specifically as n is approaching infinity. So we can use this basic set of basic facts to come up with some limits in number 5.